First grade expectations in the Common Core involve students in working with considerable variety of problem types. To ensure that your learners are getting the full scope of problem types, it is first necessary for us to understand the distinctions between them. This is a brief orientation. Here we're of course in Standard 1 in the OA domain, and the cluster that we're looking at is called Represent and Solve Problems Involving Addition and Subtraction. This cluster actually has two standards in it. Also Standard 2 will be addressed a little later in this presentation. First, Standard 1, if you look through it carefully, you'll see that it illustrates a considerable variety of types of problems that first graders are expected to work with. The situations that are listed in orange are those that will be the focus of today's lesson. This image is part of a bigger chart of problem types that first graders will be expected to solve. You will see in the left column that there are two types of action discussed in the action problem types, add to and take from. And then across the top are three possible positions of unknowns. This results in 6 problem types that can be classified as action problems. And we're going to be looking at each of these more closely. Action problems are characterized by a change in the situation. That change is associated with either a joining action, which is called adding to in the Common Core, or else a separating action, which is called taking from in the Common Core. Typically, you can think of action problems as a sequence or a chronology. You have a starting quantity, then there is a change to the set size. This change represents either an adding to action or a taking from action. And then you have a new end product as a result of the change. Action problems tend to be easier for children than non-action problems because it's easier to act out situations that involve action than non-action. I'm going to be using a phrase called situation equation, and I need to just stop for a minute and clarify what I mean by that. Below each of the word problems on this slide, you see an equation. The equation is written to exactly match the mathematical nature of the problem. If my equation is 2 plus question mark equals 5, the middle one you see here, it is true that the recognized operation for finding that answer or the solution would be subtraction. To find the solution, I would take 5 minus 2. That's called the solution equation. The one equation shown here is the situation equation. This is how you write it when it exactly matches the situation. And the situation equation is the terminology that's used in the Common Core progressions documents. Now, when we call these adding to problems, it does not refer to addition. This is probably one of the more confusing parts to think about. Rather, it's the type of action. So when you look at the examples here, you can see that when the problem is a result unknown, the first example, the column to the left, then the action, the situation in the problem, directly results in what you would call a classic addition expression. So in that case, it's addition. But if you look at the change unknown and the start unknown problems, here we also have a plus sign, which indicates that the action in the problem is joining or adding to. But it results in a missing addend problem. And missing addend problems are typically associated by adults as subtraction. However, when children begin problem solving, they act the situations out. So children themselves tend to attend to the joining action more than how we as adults would classify this particular kind of problem. In the same way that adding to problems were not synonymous with addition, taking from problems are not synonymous with subtraction. If you look at the examples shown here, note the situation equations. These equations allow us to examine the differences in how the problems are structured. If you look at the equation for the start unknown, the column on the right, you will notice that the situation equation, if we were to convert it into something that could give us a solution, would actually cause us to add the 2 and the 3. In other words, to find the original number or the whole group of apples. We would have to actually take the group that were eaten as well as the group remaining and rebuild that set to find the whole. So that's addition. So here, once again, we caution you to remember that the adding to and taking from refers to the action embedded in the problem, not the operation. Now we turn our attention to the position of the unknown and how that influences problem difficulty for early problem solvers. Recall that action problems have a kind of time sequence. This chronology is really useful to young children as they begin problem solving. Young children do not necessarily read the top problem here and think, oh, 2 plus 3 equals question mark. Rather, they actually imagine the whole situation and they use the story in the problem to help them figure out the answer. They will likely use tools such as counters or fingers to act out the situation. This represents the earliest stage of problem solving. The top problem here would actually be considered easy by most first graders. First, the action in the problem is very clear. It is easy to figure out the starting situation, easy to figure out what the change in the problem, change in that starting quantity is, and then if you just follow that, the result will emerge. The easier a problem is to act out, the easier it is for children to solve. The second reason why this is really going to be easy for most of your learners is that the number set sums to 5. The Common Core authors have specified that children exiting kindergarten should be fluent in number combinations up to 5. It should be a big focus of the kindergarten work. So many of your learners wouldn't necessarily have to act out this problem because the number sets should be so familiar to them. However, if you upped the numbers to, let's say, 16 bunnies and then 5 more bunnies hopped on over, then you might actually see them going into a modeling strategy. Result unknown problems are primarily easy for children because they simply can follow the action sequence and it will get them to the answer. Change unknown problems are more difficult for early problem solvers than the result unknown problems because they require a bit of planning to act out. For example, in the add to problem shown here, I start with 2 bunnies. Some more bunnies hop there, and then I end with 5. I can build my starting quantity of 2 bunnies, but now I have to get it to add up to 5. I can keep adding to it, but I have to keep track of the new things I add and keep them somewhat separate from my original items, or I won't be able to tell how many I'm adding. So you can see that adds a little complexity to the counting process, and that complexity is what makes change unknown problems more difficult than result unknown. Often children will build onto their original set, just keeping it a little bit distant from the original so that they can keep track of the change quantity. Knowing that change unknown problems are more difficult for children, my recommendation is that when you introduce them, drop back your number sets to make them more familiar and make sure that the context of the word problem itself is one that's fairly familiar. That may require you to do some rechanging to the wording of the problems in your curriculum to make it more familiar contextually to your own learners. These changes will allow your learners to focus on the complexity of acting out the situation rather than having to deal with the cognitive load of the unfamiliar number sets or the unfamiliar context. Then, as they grow more familiar or comfortable with the format of change unknown problems, then you can start to create more complex number sets for them. Start unknown problems are the most difficult types of action problems. First grade children are expected to work with these types of problems, although not all of them will master this problem type. Young problem solvers follow the action exactly, and they represent all of the quantities in the problem. But in this problem, they are stymied right away by the starting situation. Their default mode will be to start with the beginning amount and to build that set as they act out a situation. In this case, they can't really build an original set unless they choose a random number to start with, which is called trial and error. And the students who are likely to be successful very likely start with that process. But the fact that they don't know how to get started on the problem because they don't know the starting quantity causes these problems to be a real bear for most first graders. Often when students struggle with the problem, we make an assumption as teachers that they just need a lot of practice. I have to tell you that children's difficulty with start unknowns goes beyond mere practice. I suggest that you support students in their early efforts by actually going around through the back door. And that means looking at some other fundamental things that can help them. One of those, of course, is to do similarly to what we did in the change unknown problems. Choose lower number sets that represent really familiar numbers to them. Another one is to make sure that when you choose those numbers, you choose numbers that they have really good part-whole relations for. What I mean by that is you choose a number that they can easily generate combinations that make up that number. So in the example here, look at the take from problem. Some apples were on the table. I ate 2 apples and then there were 3 apples. How many apples were on the table before? In this case, the answer is 5. And I wouldn't have too much trouble with that if I was so familiar with 5 that I just knew 2 and 3 are 5. If I have 2 eaten and 3 left over, then that would make 5. Because I easily know that 5 is 2 and 3, 1 and 4, 4 and 1, 3 and 2, 5 and 0. If I can easily generate all the number combinations for that number, I'm said to have some pretty good part-whole understanding of that number. So I would choose number sets that represent that kind of part-whole understanding for children when they work with these start unknown problems. I certainly wouldn't give them the kind of number sets that they can work with when they have easier problem types. This chart is part of a larger one found on page 9 of the Common Core Progressions document that is associated with this domain. I include this portion here because I want you to notice the shading that's used. The result unknown problems are shaded dark gray, and that indicates in the key that kindergarten children should have been exposed to these. So that represents what they should be familiar with when they come into first grade. Now in first grade, they're supposed to keep working with those problems, but of course, we always want to up the challenge. In first grade, we use these problems as a tool to build their strategies. Because the problem type is familiar, we can now increase the expectations for students. We're going to be looking for how we can leverage these problems to get the students comfortable being more strategic. For example, transitioning from an acting out strategy to a counting on strategy. Also, if we want to get students familiar working with larger number sets or more complex number sets in a word problem, we're most likely to start that with these problems since they're already familiar to the learners. Notice that the start unknown, the final column, is actually unshaded or white. This is in the key an indicator that first grade children are expected to work these problems. Even though they're hard, they're still expected to have experience working these problems. But the Common Core authors recognize that mastery of these problems is likely to occur in second grade. That some students will be able to manage that in first, some will still be working on that, and the goal for them will be to have it mastered in second. Okay, here you see 3 word problems. They're taken from a first grade workbook. I would like you to practice finding the types of problems. I do not recommend that you train students to type problems in this way. The actual problem type structure, the whole matrix for how we're classifying problems, is based on research for how children make sense of problems. Therefore, the kindest thing that we can do for our students is to support them in their own natural capacity to make sense of situations, rather than trying to formalize this process and make it even more difficult by training them how to determine problem types. The words that I've used with you as far as result unknown, start unknown, change unknown, this is teacher jargon. We don't use this language with children. Now, the reason that I think it is worth training you to type problems, to figure out the problem type, though, is that you actually have the responsibility of monitoring and ensuring that your first graders have the opportunity to engage with problems of all of the subtypes. So far we've learned about 6. There's more coming in the next presentation. In order to ensure they're getting this sufficient variety of problem solving, you're going to need to know how to analyze the problems in your textbook and type them. As you read each of the questions here, I'm going to have you pause the presentation in a minute, but as you read these, first decide if it is an add to problem or a take from problem. That's the first classification system that you should use. Remember that these terms do not refer to addition and subtraction, but they refer to the kind of action that's embedded in the problem. Once you've done that, now go ahead and determine whether it is a result unknown, a change unknown, or a start unknown. Go ahead and pause the presentation now and spend a moment typing these problems. Now we're going to go through each of them, and I will model not only how I typed them, but also a bit of background knowledge on determining problem difficulty. The first thing I want you to notice is that the top two problems were taken from the same page in the workbook. This is really a nice example of variety in problems on the same assignment. This type of variation keeps the students mentally alert and attentive to individual features in problems. As I looked at each of the problems, I first tried to figure out whether they represented add to or take from situations. In the first problem, a set of toy soldiers will increase in the problem. And in the last problem, a set of buttons will increase. So both of those represent joining situations or adding to situations. In the second problem, pencils are being sold. That action is a take from situation. Next, I examined the start quantities, change quantities, and result quantities. I don't normally color code them, but for ease in drawing your attention to them, I put the start quantities in blue. In the first problem, the start quantity is very conveniently located right at the first. Remember, that's the set that children will want to start with, and it shows up first. That adds to the ease of the problem. And then the change quantity comes next, very easy to follow, and the result is expected. That problem should be very easy for your learners. In the second problem, there is really no mention of a start quantity other than the fact that you're prompted to find it in the final sentence. Some questions like this that have no start and where you're searching for the start will actually begin with something like Sam had some pencils, then he sold 6 pencils. This one doesn't mention it. It's a start unknown, and it doesn't mention anything about the starting quantity to begin with. I think you can expect this one to pose a challenge for at least some of your learners. And the final question is a change unknown. The wording of the problem actually begins with a desired result. So you're beginning kind of with the end of what the problem is asking for. Then it gives a start quantity, and then it asks for the change. I would anticipate with that wording structure that that's going to be a bit of a challenge for students, perhaps not as much as the start unknown. And I would want all the students to attempt to engage with this and make sense, see if they can act this out. However, I would probably go into a lesson that involved this problem with an alternative wording in mind that would make the problem more accessible for some of my struggling learners. You're going to learn a little bit more about how to make word problems more accessible in this session on supporting first grade problem solvers. All right, now we're going to shift gears just a little bit, although it's really a natural extension from what we've already been doing, and we're going to take a look at the second standard in this cluster. The second standard offers one kind of really new thing based on everything else we've done. In fact, most of it is pretty similar to what we've just been talking about. The only difference is that there's no mention of position of unknown, and there's also a reference to using 3 addends. So the 3 addends represents the new element here. We're going to take a look at why 3 addends is significant. If it were just a minor thing, they could easily have added that as one of those many conditions that were laid out in the first standard. But instead, they've given a second standard to this and dedicated it specifically to problems with 3 addends. By this, you can kind of conclude that the Common Core authors believe there's something particularly special that children can gain by experience with 3 addends, and that's what we're going to explore next. When children work with problems that have 3 addends, it raises the idea of whether order matters. Does it make a difference if I add the 3 and the 8 and then add on the 7, or if I add the 7 and the 3 first and then add on the 8? This dialogue gets the students thinking about the any order property of addition, and it also leads to a great strategy discussion around the idea of efficiency. If both ideas of solving it work, are there any advantages of one approach to the other? Is one easier to do mentally or more efficient than the other? In the example above, it is typically easier for children to solve the second equation mentally because it rearranges the addends to make 10, and then 10 and 8 is 18. Making 10 is a strategy that is specifically mentioned in the Common Core and which we'll be discussing next week. Another aspect of problems with 3 addends is that it increases the number of possible solution methods that children will use to solve them. This can make for some really excellent strategy share sessions with children. For example, I've included a video clip in the Teaching Resources section for this lesson that shows a first grade math talk, or a portion of one. You see how the teacher is using a three-addend situation to support students' capacity to reason quantitatively and to foster peer listening, a skill that will be necessary for them to critique the reasoning of others. This references the second and the third standard of mathematical practice. Problem solving is intrinsic to the nature of mathematics and should be present even in our work with very young children. The standards of mathematical practice make this clear. It would be impossible to fully address the standards of mathematical practice without a curriculum that incorporated a fair bit of problem solving. As we look at these particular standards, consider whether your current approach to problem solving addresses them. In the first standard, we look at making sense and persevering. If you have to tell students what operation to use, you automatically know that they are not making sense of the problem. If, on the other hand, they are able to discuss how the situation relates to a diagram or to what they acted out, and if they can point to the parts of an equation and explain how the equation and the parts of the equation represent parts of the original situation, then you are addressing the standard. As they make sense, children are more likely to persevere. When children don't make sense, they want to give up. Ultimately, problem solving is about making decisions. If students have no decisions to make, then it ceases to be a true problem. The students should be making decisions about how to represent the mathematical relationships in a problem, for example, through manipulating objects or a drawing and an equation. They need to make decisions about how to use these tools. As you give them more difficult problems, like change unknown and start unknown problems, it becomes more and more important for them to give careful consideration about which tools to use and how to use them to represent a situation. I strongly suggest that the Carpenter, Fenema, Franke, Levy, and Empson book, Children's Mathematics Cognitively Guided Instruction, be added to your collection if you are really feeling like you need some additional work on thinking about problem